Question number 1 says, the following compound with the molecular formula C4H8O2 is an ester. Give its structure and assign the chemical shift values. So where should we start here? Well, first of all, we know there's 8 protons in the compound. So since it's C4H8, there's 8 protons. And we know that it's an ester. So we know that somewhere in the molecule we must have a carbonyl attached to an oxygen like that. That would be an ester. I mean, you could put an R group here and an R group here. But we need to determine exactly what those R groups are. So I'm going to remove those for now. And then we're going to take a look at the integration. So if I look at the integration, this integration isn't given to us in step curves. It's actually given directly to us on the spectrum, which is kind of nice. So it says here the integral here is 2. So that means there's going to be 2 protons here, or the area under this quartet would represent 2 protons. This one here is 3, so that would represent a ratio of 3 protons to the first 2 protons that I circled, and the last one is 3. And also what's nice about this integration is that we don't have to do any special kind of math, because you can see right away that if we assume that this is 2 protons and that this peak represents 3 protons and that this triplet here represents 3 protons, well, you can probably add up 2 plus 3 plus 3, which gives us exactly 8 protons. So there we go. So we know that the integration's already good to go. We know that our first peak here, it's centered somewhere around what? Around 4.2-ish. The next one is a singlet. That looks like it's centered. Oh, that's not very good. But anyhow, it looks like it's centered somewhere around 2.05 ppm maybe. Anyhow, let me write in the first one around the quartet. So that looks like it's maybe around, I don't know, 4.15, something like that. Okay, and the last one, the triplet here, that looks like it's centered around, I don't know, 1.1, 2, 3, maybe 1.12, maybe 1.25, I don't know, something like that. So we'll put around 1.25. So those are the chemical shifts for those 3 signals. And obviously the one with the highest chemical shift, that's the one that's the most deshielded, and the one with the lowest chemical shift, that is the one that is the most shielded. So if you remember the table that we would have looked at in 3101, table 15.1, so I'll write that down here, table 15.1 in Klein, the 3rd edition, gives some really nice pointers on how to estimate chemical shifts. And if you remember, if you were to have a CH2 group here next to this oxygen, okay, if we were to put a CH2 group there, a CH2 normally has a chemical shift, so a methylene normally has a chemical shift of about 1.2 parts per million. But if we add 3 to that, because it's next to the oxygen of an ester, we would end up with about 4.2 parts per million. So that lines up pretty close with our 4.15, and it would make sense that that would be a quartet, because if we had that next to a methyl group, okay, because of the n+1 splitting pattern, these 2 protons would be split by these 3 protons. So 3 plus 1, so if I go back to the n+1 rule, 3 plus 1 would be 4, and that is why we get a quartet here. And for the methyl group, so this methyl group here, so let me just get rid of that. Anyhow, so for that methyl group, a methyl group normally comes out around 0.9 parts per million. And since we're beta, so this is the alpha carbon here, alpha to the oxygen, and this one is beta to the oxygen, we're going to add 1/5 of 3. So that would be 0.6. So we take 0.9 and we add 0.6 parts per million. I didn't include the units, but anyway, we get around 1.5 parts per million. So that makes pretty good sense too, because our triplet down here, our triplet is around 1.25. So that's a pretty good estimation as well. And then the last one, the last peak here, this is the singlet. That represents 3 protons, and that makes, it seems reasonable, because this methyl group, the protons on that methyl group aren't coupled next to any protons at all. Therefore, they're going to result in a singlet. And since they're alpha to a carbonyl, we're going to add 1 to the chemical shift of a methyl group, which we already said was 0.9. So it would be 0.9 plus 1 part per million. So it's going to be around 1.9 parts per million, and that lines up pretty good with our 2.05. So there we go. We've assigned each one of the peaks, and we've elucidated the structure of the compound. There's just one more thing I want to cover here, and that's proper annotation of an NMR spectrum. So the proper way to annotate an NMR spectrum is such that everybody in the class should annotate the spectrum in the exact same way. And the way that is we start at 0 ppm. So we start down here and we go from upfield and then we travel downfield. So we go from upfield to downfield. So we put up here and we keep going to downfield. And what we do is we label each series of peaks with a letter of the alphabet. So we'd start here with the first group of peaks. So the triplet, we'll label that A, the singlet will be B, and then the quartet will be C, like that. And if we had more peaks, we would label them, D, E, F, and so on and so forth. So then when we go back to our compound up here, so the compound that we've elucidated the structure of, we're going to label the triplet. We're going to label those protons with the letter A. So we'll put the letter A next to that methyl group. Then the quartet, so these peaks here, the quartet, we're going to label those C. And then finally, the singlet will give that the annotation B, like that. So if everybody, and this is the proper way to annotate the spectrum, if everybody labels the spectrum going from upfield to downfield, A, B, C, D, so on and so forth, then all molecules should be labeled in the same way if they're done correctly.